Hello everyone, my name is Shiva and today I'll be presenting our work Quantifying, Characterizing and Mitigating Flakily Covered Program Elements. In our work, we take a closer look at code coverage. Code coverage is a measure of test adequacy. It tells you if you have written enough tests for your code. How is code coverage calculated? Let's look at an example. Consider this piece of source code. Coverage tools work by identifying all executable statements in your source code. Then, they run the test suite to determine which statements get executed. Finally, code coverage is repeated as the percentage of statements that get executed. High coverage implies that a large proportion of the code base has been tested. Thus, coverage is often used as a quality gate in continuous integration pipelines. But coverage is not a perfect measure. Low coverage means insufficient testing. High coverage guarantees nothing. In fact, previous studies have established coverage is not strongly correlated with test suite effectiveness. Why is that so? Because code coverage considers all tests to be equal while the reality is different. For example, sometimes tests can be flaky and that is not accounted for in coverage. What is a flaky test? A flaky test is a test with non-deterministic behavior. Here's an example. The problem in this test is this sleep statement right here. Because of the asynchronous nature of wait introduced by sleep statement, the first time you run this test, it might pass, and the second time you run this test, it might fail, even though you haven't changed the code or a test. This is a flaky test, and this reduces the confidence of your developer in the test suite. Any statement that is covered only by flaky test should be considered risky. That is the core idea of our study. We study these flakily covered statements in the wild by studying 3 projects from the OpenStack ecosystem. To collect the data for our study, we start by first collecting statement level coverage with the test to statement mapping. Then, from the project's CI history, we collect a list of flaky tests. Finally, we combine this data to tag the statements that are flakily covered. By flakily covered, we mean statements that are covered only by flaky test. For example, here, statement 3 is tagged as flakily covered while statement 2 is not, because statement 2 is covered by test T1, which is not a flaky test. Now that we have tagged the flakily covered statements, we study these statements with 3 objectives in mind: to quantify, to characterize, and to mitigate. Let's look at quantification. To what degree are program statements flakily covered? Here's the split for the Neutron project. We can see that about 10% of statements were flakily covered. We observed between less than 1% to 10% of flakily covered statements across the projects we studied. Now that we know the occurrence of flakily covered statements, we move to the next step, which is to characterize. We want to identify if these flakily covered statements can be distinguished from robustly covered statements. To do so, we introduce the devil of the story, who says that there should be some code characteristics that identify flakily covered statements. We take the position of a devil's advocate and explore if we can explain the occurrence of flakily covered statements through some basic code characteristics such as dispersion, ownership, and development activity. For example, as the devil's advocate, we say, maybe the flakily covered statements are all from a networking module that is hard to test robustly. To see if that is the case, we count the number of flakily covered statements from each module and construct a tree map. We see that there are some hotspots, but generally, flakily covered statements are dispersed across various modules of the project. Then we say maybe it's the new contributors who are writing code that is difficult to test robustly. So we study the distribution of experience across flakily covered statements and robustly covered statements and find that the distribution is similar and nothing really stands out. Then maybe we say maybe the flakily covered statements are because of development activity. Maybe it's because of the statement age or the statement churn. So we compare the statement age and churn across the flakily covered statements versus robustly covered statements. We compare the distributions using the man with neo statistical test. Although our p-value is less than 0.001, which indicates that the distributions are statistically different, the Cliff's delta size is negligible or very weak, so the practical difference is insignificant. Our devil's advocate couldn't make anything stick, so we will move on from this now and focus on prioritizing flakily covered statements for repair. So how do we select which test to repair? How do we prioritize a test for repair? We propose a greedy approach for prioritization. Consider a list of flaky tests to be repaired and the list of flakily covered statements that will be repaired by fixing the test. We rank the tests. Higher the number of statements fixed, higher the rank. We propose the highest rank test for repair. We assume that the test has been fixed and then we rank the remaining tests for repair. In this iteration, T3 now offers the largest return, so that is suggested for repair. We compare the GreedyFlake with other prioritization approaches. We establish a random baseline. We establish a baseline with the random approach where we randomly select a flaky test for repair. This is our baseline approach. Then we compare with total statement coverage where we select the test that has the maximum coverage first. Then we have additional statement coverage, which is total statement coverage but with a re-ranking step. And then we use total flaky statement coverage. We select the test that has the maximum flakily coverage statements first, which is GreedyFlake without a re-ranking step. And then there is GreedyFlake in and of itself. To compare these approaches, we compute the area under the cost effectiveness curve. On the x-axis, we plot the number of flaky tests repaired. On the y-axis, we plot the percentage of flakily covered statements repaired. We plot our curve and we compute the area under the curve. We repeat it for all approaches. Higher the area under the cost effectiveness curve, better the approach. Here's the result for our projects. We can see that GreedyFlake has the highest area under the cost effectiveness curve. Here's the detailed comparison. GreedyFlake outperforms all the approaches, but comparing it with just the total flaky statement coverage, that is without a re-ranking, we can see that most of the benefits can be achieved by just targeting the flakily covered statements, and there is no need to be greedy. So now we have quantified, characterized, and mitigated flakily covered statements. What can we do next? For practitioners, a good idea would be to integrate enriched coverage into their workflows. For researchers, we can explore the relationship between flakily covered statements and other code characteristics such as code complexity and readability. We can expand coverage by adding other test characteristics, for example, test smells. So that is our study. Our core idea was that all tests are not equal and that should be reflected in coverage. We studied flakily covered statements and quantified, characterized, and suggested a prioritization approach. And we have some implications for practitioners and researchers. This is Shiva from the Software Rebels Lab. Thank you.
Hi everyone, welcome to this session titled Flaky Tests. My name is Jose Rojas and I will be your session chair today. You have just watched the presentation for the first paper titled Quantifying, Characterizing, and Mitigating Flakily Covered Program Elements. This is a first journal paper published in TSC last year, and we have the pleasure to have Shiva Subramanian here with us today to answer the questions that you might have. Hi Shiva. So please start popping your questions in the chat. I will start with our first question that has been posted by Jonathan Bell. Hi, John. Very cool study. Are there any tests with flaky coverage that are just going to intrinsically be covered flakily in a way that can't really be changed or repaired?
Yeah,
Yeah, flaky tests are difficult to repair. Certainly, there are sometimes, especially when you are doing large tests, large integration tests with a lot of different components, sometimes it can be difficult to repair. But I don't know if there are ways in which you can identify the flakiness and you could mitigate. It depends really upon the cause. I have not come across a flaky test that cannot be fixed. Certainly, it can be difficult to repair. There might be a lot of refactor involved, but I'm not sure if there is any flaky test that cannot be repaired.
Jonathan says, thanks. We have a question from Ahmad Abdelatif. Very nice presentation, he says. I'm not sure if I missed it, but how did you identify the flaky tests to build the corpus using the study?
So we took projects from the OpenStack ecosystem. Basically, we collected the list of flaky tests from their CI history. So in their CI system, they have the ability to rerun the test. So developer itself can initiate a test against the patch that they submitted. So if there's a failure, they could like just type in a command and they can rerun the test. So we identified all the places where the tests were rerun, and then we went through the test run and saw like what passed and what failed. We saw if there was any change in the results, and that's how we identified the list of flaky tests.
Perhaps I can follow up on that one. What was your threshold to decide that a test was deemed flaky? Did it have to permutate the outcome just once and that was enough? Or did you?
Yes.
Perhaps a follow-up to that then again is, did you consider using some of the existing tools, like for example, Jonathan's very good tool, GreedyFlake, to detect flakiness instead of relying on historical data?
So we just wanted to explore an alternative source and see if we could like figure out from the project CI history. We had that, so we went with that. But I am very familiar with GreedyFlake, and I did use the tool. I did explore the tool initially when I started out with the study. So I think the tool was written for Java. I couldn't find, and the OpenStack system that we were studying were like Python, based on Python. So at that time, I couldn't make that work. Yeah.
Great, thanks. Any more questions from the audience? While more questions pop up, I'll put my test generation hat on, and I will ask if you ever considered using, for example, test generation in order to recover coverage of these flakily covered lines. So imagine you have a flaky test and these lines are not covered otherwise. Perhaps you could generate test cases using automated generation. These tests will likely not be flaky, and perhaps you will achieve the same or higher levels of coverage on this code.
Sorry, can you please repeat the question again? I lost like bits of it.
Yes. You could potentially try to recover the coverage that you lose by dropping flaky tests with test generation tools. Did you consider that possibility, or do you have any thoughts about that?
It's not an area that I'm terribly familiar with, automatic test case generation, but I'm going to say why not. It's a certainly and a good goal to work towards, I guess. Yeah.
John offers his help to work with you there. He's saying that he has some examples from his work in ASC 18 where perhaps you could compare results or insights, perhaps.
Yeah, that would be actually really good.
Yes.
Yeah.
More questions from the audience? So if not, perhaps I could ask if there is any, let's say, pressing ways forward after this for this work. How do you envision this work moving forward after this, let's say, body of knowledge that you have developed?
So one of the things that we had for like practitioners was that like we wanted to see how it would look like if we integrate this into their coverage workflow. So instead of just pass or fail, we could also indicate it's a flaky test. So one of the things that I think as a practitioner like right now would be useful for me is that it might help me identify what are the paths that are taken by flaky test, and it might actually be a way for me to go and fix my flaky test if I know like this is all the code that my flaky test is touching. The other thing is for researchers, we looked at only basic code characteristics in our study. We could look at like different characteristics. One of the things that I was particularly interested in exploring was test smells, the relationship between test smells and flaky tests. There have been some studies in that aspect, but if we could, uh, so that would be an interesting study to see if we could like see the relationship between test smells and flaky test and see how that affects the flakily covered program elements. So different code characteristics that could be studied. So that's one direction that we could take.
Not that you mentioned this, there is no more questions, so I have the opportunity to keep asking my questions. So imagine that you spot this. Okay, there is one. I'll hold mine. Gary Levens asks, are some tests flaky because of the code they are testing, or is it flakiness, or is it being flaky a property only of the test itself?
So it is both. Sometimes it's the test that's written like in a way that it's flaky. Sometimes it's the code that is hard to test. So that's why in our study, when we were looking at the especially the ownership and the development characteristics, we looked at both the test code itself and then the code that it was testing. So it is both. I know I'm sorry, I forgot the authors, but there's a paper, I think it's an empirical analysis of flaky test where they list like the 10 major causes of flaky test. It's a really interesting paper and it's a really good paper.
Luo et al, I think.
That's the one. Yes. Yeah. Yeah.
Yes.
So they list
nice.
the cause, but the answer is yes, it is because it might be because of the code or it might be because of the test. It's not intrinsically a characteristics of the test.
So we only have 1 minute left for the Q&A. Have you thought of combining this with mutation analysis?
No, not really.
Imagine that you have some tests, some lines that are only covered by flaky tests. Find the mutants that are on those lines, then use test generation to produce test cases that kill those mutants, and then basically you have good tests that achieve same coverage and that preserve some fault detection ability.
That sounds really cool.
To know? Maybe. Yeah. Anyway, that's an idea, perhaps. Thank you very much, Shiva. Very nice, very nice work and very nice presentation. And thanks for all the answers. For everyone interested, Shiva will be in the discussion room after this presentation. So you will have the opportunity to join her in the discussion room as soon as this Q&A is finished. And for those of you who want to stay in the session, our next paper is called Flake Flagger, Predicting Flakiness Without Rerunning Tests. Very nice paper as well. So I look forward to talking to you in 10 minutes after that presentation. Thank you very much. And thank you very much, Shiva, for your work.
Thanks, everyone.